Good morning, everyone. I'm Megan Kevel, co-coordinator for the Northern Rockies Fire Science Network, which delivers science and provides opportunities for engagement between managers and scientists about critical fire and fuels topics. On behalf of our team and our partners, I want to welcome you to today's webinar, Effects of Fuel Treatments and Previous Fires on Subsequent Fire Management Costs, with Kevin Barnett. This webinar will feature research conducted by Kevin and his colleagues, Helen Naughton, Sean Parks, and Carol Miller. Before introducing Kevin, I'd like to review a couple of webinar housekeeping items. Everyone is in listen-only mode for this webinar, but you can ask questions of me or Kevin by typing them into the questions pane of the control panel at the right of your screen. These questions will help facilitate discussion following the presentation. Whatever you do in your control panel does not affect the presentation, so feel free to type a test message or test your audio at any time. A recording of this webinar will be available on the Northern Rockies Fire Science Network website and our YouTube channel soon after the conclusion of the live webinar. And with that, I'll move on with introducing our presenter, Kevin Barnett. Kevin is a research associate in the Department of Economics at the University of Montana in Missoula. Kevin received his undergraduate degree in economics and his master's degree in forest management, both from the University of Montana. His research interests are in the economics of natural resource management and policy, with a recent focus on wildland fire and fuels management. Welcome, Kevin, and thank you for being here today.
Thank you, Megan, and thank you everyone for attending this morning. It's a privilege to be here. Sharing the results from the 3-year project that we've been working on. Before I get going any farther, though, I would like to thank a few people. Thank you, Megan, and thank you to Vita Wright for hosting this webinar. And I'm here on behalf of a group of us who performed this research, the first of which being Helen Naughton, Associate Professor in the Department of Economics here at the University of Montana, also the PI on this project, as well as research ecologists Sean Parks and Carol Miller from the Leopold Institute. It's exciting to be here right now, culminating this project. When we look back and think about, we had these ideas a few years ago that we wanted to explore, and it's really cool for someone like me to come out of graduate school and directly participate in the project from idea conception to now sharing the final results. So thanks to you three for being a part of this adventure. I'd also like to thank a series of people who were instrumental in sharing information with us throughout this project, the first of which being Carla Shamber from the Washington Office of the Forest Service. Carla spent, I know, a lot of her own time accessing and acquiring the daily fire management cost data, which served as the cornerstone for this project. So thank you very, very much, Carla. Next is Lisa Holzinger from the Leopold Institute. Lisa also shared a whole suite of spatial data sets with us, as well as several scripts to process those data, and was very helpful along the way. Next is Dave Culkin and Crystal Stonesifer from the Rocky Mountain Research Station, who were very willing and very prompt in sharing a whole bunch of suppression resource order data, which they've become experts in. That data was very helpful for us. It served as a really important backup, and is also, we hope to leverage here in the future with several subsequent research questions that we have. Next is Matt Thompson and Karen Riley, also of the Rocky Mountain Research Station. Matt and Karen and Helen and I co-organized a session in Reno this past spring at the Cohesive Management Strategy Workshop, where we try to get as many good balance of science and managers there to talk broadly about fire and fuel treatments. Matt and Karen were instrumental in reaching out to folks from various agencies to get them to participate, which was, for us, a great venue to share this research for the first time. Thank you, Matt and Karen. And lastly is Matt Jolly from the Missoula Fire Sciences Lab. We leveraged a gridded spatial fire weather data set from Matt that was really important in this analysis. Thank you very much, Matt. And also, obviously, our respective institutions and all the support that we've had from them over the past few years. Thank you. So when I think about this research, I think first and foremost, it has its roots in evaluating policy. And as economists, or those like myself who like to play economists, we're really interested in applying empirical methods and quantitative methods to evaluate policy. So those of us here are all well aware of, I'm sure, that fuels management is both a necessary and critical component to achieving the goals set forth in the National Cohesive Wildland Fire Management Strategy. And I'm just going to list 3 ways in particular. The first one is that we have many areas throughout the United States that have been degraded by prior management, whether that's through the successful suppression of wildland fire or through other historic land management practices. And fuels management is very helpful in restoring the structure and composition of those ecosystems, especially moving forward into the future. The second is that in many areas where we would like to use fire to achieve land management objectives, we first must restore, like I was saying, the structure and composition of these forests and forested ecosystems prior to the subsequent use of fire. And so we can think about fuel treatments as sort of setting the stage for the future use of fire. And lastly, and most interesting to us, hope you can all hear me still, sorry. Lastly, and most interesting to us is this idea and this notion that hopefully we can use fuels management as a tool to facilitate the long-term reductions in wildland fire management costs, which those of us here, I'm sure in attendance, have seen a figure somewhat like this, where on the y-axis we see suppression expenditures plotted in millions of dollars, and on the x-axis is time, going from 1985 to 2016. I have 3 trend lines here plotted. The first one is the green line, which is just for the USDA Forest Service. The gold line is all of the Department of Interior agencies together. And then the gray dash line is the 10-year moving average just for the USDA Forest Service. And there's a few things of note here. Obviously, we see increases in annual suppression expenditures for both the Forest Service and the Department of Interior agencies, with a particular notice increase or departure for the Forest Service trend line. In fact, from 1986 to 2015, over that 30-year period, we've seen an order of magnitude increase in annual wildland fire suppression expenditures for the Forest Service, from around $150 million a year in 1986 to over $1.5 billion in 2015. Now, of interest is with this gray dash line of the 10-year moving average, is the 10-year moving average, so the average annual suppression expenditures over the 10-year period. That metric is used in part during budget allocations for wildland fire. And so we can see that there are years in which the realized expenditures exceed the 10-year moving average. And when we experience these events, the agency is required to reallocate or shift money from other programs to offset the difference in actual expenditures and appropriations, which is a term that we've been calling fire borrowing over the years. And there's some interesting effects of fire borrowing, including that's documented in this report, the rising cost of wildfire operations effect on the Forest Service's non-fire work. And the point of this figure right here is I've plotted the % reduction in budgets from 2001 and 2015 for these 8 non-fire programs within the Forest Service. And we can see, for example, 3 of these 8 programs, we've seen an over 50% decrease in allocated monies, including one of those 3 being land management planning, which includes efforts to revise and update forest land management plans to include best available science, and so on and so forth. So the point here is just that the increase in wildland fire suppression expenditures definitely has an effect on the Forest Service's ability to achieve its non-fire management objectives. So there's been several ways in which folks have proposed to curb this increase in wildland fire suppression costs. I'm going to mention 4 of them real quick. The first one is to, well, let's just reform the way in which wildland fire is budgeted. Let's move fire away from the current model, its annual appropriations, and treat wildland fire similar to other natural disasters, move it underneath the branch of FEMA. The second is to enact local zoning laws to limit the growth in the wildland-urban interface, which is an often cited driver of the increase in wildland fire management costs. The idea here being that is that if we shift the incentive structure around from the federal level to the local level, perhaps local governments will then be incentivized to curb ex-urban development in hopes that then we can achieve long-term reductions in fire management costs. The third is to reduce the frequency of human-caused ignitions. There's been several large, very expensive wildland fires that are started by humans, particularly in the southeastern United States. This is a very prevalent issue. And I want to make sure I give credit to all these three first, because moving forward, we're going to move away from these three, and we're going to talk about a fourth pathway to reduce wildland fire management costs. All of those have their value in these discussions, but we're going to focus on the management of hazardous fuels. In particular, three ways in which it's been hypothesized that hazardous fuels management can influence long-term wildland fire management costs. The first one being that it can simply increase the likelihood that we'll be successful at suppressing fires during the initial attack phase. In the short term, it's been argued that successful initial attack is the most appropriate way to achieve short-term reductions in wildland fire management costs. The second is that when we do engage the fire, previously treated areas can be leveraged to enhance the likelihood of containment when a fire reaches a previously treated or burned area. And that's been qualitatively noted in the fire community for a very long time, and it's also been quantitatively discussed in some papers. And lastly, if we step back a little bit farther, is this idea that in the long term, however, fuel treatments can be seen as a vehicle to expand the decision space that managers have when they're faced with a future unplanned ignition. That is, when we get an ignition in an area that has received treatments, fire managers will not simply be forced to immediately suppress those fires. We can manage them, and we can use fewer resources, achieve our land management objectives, restore the use of fire, and achieve long-term reductions in fire management costs. So let's go ahead and talk about what it is that we already currently know about what drives wildland fire management costs. I'm just going to talk about a few kind of broad things real quickly. The first one being a group of biophysical variables, whether or not ignitions ignite in certain fuel types, timber versus grass. Extreme fire weather, as captured through the energy release component, has been shown to be positively and significantly correlated with wildland fire management costs, as well as different ways to characterize topography. Things like elevation, aspect, and slope. Very importantly, however, are the values at risk that are present throughout the landscape. It's well understood in this little body of literature that the presence of private infrastructure in particular is a strong driver of fire management costs. Not only is it simply the presence, however, of private infrastructure, but also it's been found in a recent paper by Clark and others that the spatial pattern of those values can have different effects on fire management outcomes. And lastly, there's a group of variables that can be characterized under the fire management heading, whereas that are reflective of policy and other sort of dimensions of fire management, such as whether a fire ignites in wilderness or other protected areas where the use of fire might be encouraged. There's a nice new paper out from Michael Hand and others that found that a fairly sizable proportion of the variability in fire management costs can simply be explained by understanding the management teams that were responsible for those fires on a given day. So, however, it's important to note here that there still remains a whole lot of variability in fire management costs that we can't explain with our best statistical models. There are things like incentive structure, risk aversion, experience, socio-political pressures that are challenging to incorporate into these modeling frameworks. Furthermore, we have only a limited understanding of the role of fuel treatments in previously burned areas on fire management costs. There has been some great work on this done already, largely due to data limitations or data access. we've used these simulation frameworks and comparative modeling approaches to estimate the impacts of fuel treatments in previously burned areas on future fire management costs. The idea being that we can simulate fire and vegetation change over time, and we can see how that responds to changing landscape conditions, or you can interpret that as, what the landscape might look like had we implemented a series of fuel treatments or had allowed previous fires to burn. And then we use previous regression equations that we can use to estimate the effects of those changing landscape conditions on fire management costs. For example, using an equation developed by Chris Together and others to estimate fire costs. In particular, however, we've used changes in fire size and fire severity, for example, as the causal mechanism to link the effects of fuel treatments in previously burned areas on future fire management costs. That is, because we've established previous relationships with fire size, severity, and future fire management costs, if we see a change in those other variables, we can then infer how that might affect future fire management costs using those developed associations. I think there's a couple of factors that we wanted to address that we saw as hopefully our ability to contribute to this body of literature. The first one being, like as I said, these treatment effects are linked to correlated outcomes such as changes in fire severity, as opposed to trying to understand a little bit more of the direct link between fuels treatments and future fire management costs. I think largely, we've been limited by access to finer temporal scale wildland fire management cost data, so we've used aggregated fire level data. And what that means is that we're unable to examine how decision-making changes through time as a function of changing landscape conditions. And ultimately, if we're going to be trying to tie decision-making within a wildland fire event to the environment around it, we're going to need to leverage daily fire management cost data. So that brings us to the objectives of this research. And real simply, our goal here was to evaluate fuel treatment in previously burned areas, the effects of those on daily fire management costs. You'll probably hear me say the word daily quite a bit throughout the remainder of this presentation, but it should be noted that the temporal unit of analysis here was a day of a fire. We had a couple of working hypotheses that formed this, the design of this study, really. The first one being simply that encounters with fuel treatments or previously burned areas result in a decrease in daily fire management costs, holding all else constant. And then a second hypothesis that we formed was that the effects of fuel treatments in previously burned areas on daily fire management costs differ. That is, it's been noted now, and there's been a ton of great work recently that's shown that previously burned areas can function as natural fuel treatments from a variety of perspectives. And because it's also recognized that that wildland fire affects such a greater extent of the landscape relative to fuel treatments, we think that there just might be a different effect of fuel treatments in previously burned areas on future fire management decision-making and future fire management costs. So in this study, we've explicitly distinguished the effects of previous fuel treatments and previously burned areas on daily fire management costs. So how did we go about doing that? Well, we first needed to basically draw big lines in the sand to start with identifying our sample frame. What were the fires that we could even evaluate? So what we did for that, just real briefly, is we first grabbed all the fire parameters from the monitoring trends and burn severity data set, grabbed a fuel treatment geodatabase that is maintained by Landfire that is used in part to update their vegetation and fuel products, and we identified all the recent fires that had burned into a previously burned area or a previously treated area. And that was our first spatial filter you could think of. And in that process, just doing that in and of itself resulted in our ability to then summarize, in terms of fuel treatments, the frequency, extent, and geographic variation of encounters of recent fuel treatments and subsequent wildland fires. We had that summarized and published in a recent paper. We also then filtered out all of those possible fires based on whether or not those fires were at one point managed by a Type 1 or a Type 2 incident management team. And that was because we obtained daily fire management cost data from the Forest Service's iSuite database. And those data are only retained for fires that at one point were managed by a Type 1 or a Type 2 team. We tried our best to make sure that we also only retained fires that were predominantly managed by the Forest Service, although we recognize that there are other agencies and groups involved in managing wildland fire events. Next was an important step where we mapped the spatial progression of each of our sample fires using a spatial interpolation technique that Sean developed a few years back. This allowed us to delineate for each of our fires in a consistent manner where we think these fires were the footprint of a fire at every given point in time as a fire spreads across a landscape. And you can understand why we wanted to do that, because we wanted to then extract and summarize all of this spatial data underneath those fire footprints that we thought were important drivers of the daily fire environment and that drove decision making and fire management costs. So I'll go through that here in a second, all the different variables that we used and summarized to explain daily fire management costs within those daily footprints from the fire progression maps. And lastly, we built econometric or statistical models that explained variation in daily fire management costs. And the goal with that here is to include a bunch of information that we think is important in explaining variation in daily fire management costs, but then include information about encounters with previous fuel treatments in previously burned areas in order to isolate the marginal effect for days in which a fire encounters one of these previously treated or burned areas. So again, try our best to acquire information that can capture as much variability in daily fire management costs as possible, include variables that describe encounters with previous treatments or fuel or previously burned areas, and try to isolate those unique effects. So we ultimately received daily fire management cost data for 56 fires located throughout the lower United States, which is depicted here in this map. These are the ignition points for each of our 56 fires, and the size of these circles is scaled to the final area burned. Just for an example, we had final area burned ranging from about 500 hectares to over 121,000 hectares. You can see, however, that we were mostly able to get daily fire management cost data for fires located in the western United States. We had some big fires in Southern California, in the northern Great Basin, as well as scattered throughout the Rockies and the Pacific Northwest. We were able to also obtain a few fires located down there in the Southwest, and like I said, 4 located in non-Western U.S. ecoregions. So for each one of these fires, we mapped daily fire progression. And so this slide is going to give you just a quick and dirty example of how we went about doing that. On the left panel here, we see MODIS hotspot fire detection data. And these data are great in that they have a relatively coarse spatial resolution, but they have a relatively fine temporal resolution because the satellites that detect these hotspots pass overhead several times a day. So these Julian days, or the day of burning, are color-coded from red to blue, ranging from early in the fire's progression to then later. So using a spatial interpolation technique, we can then produce a continuous raster grid of what we're calling day of burning, what Sean calls day of burning. And these represent the daily area burned as a fire spreads across the landscape. So using this information, we can know where a fire was at any given point in time. And so you can think about, there's all these other spatial layers underneath this map right here that we then summarized within the cumulative footprint as a fire spreads across the landscape. So let's go ahead and talk about what it is we included in these statistical models. You can think about this as being 3 or 4 major groups of variables. The first one being the management context of the fire environment, the second being variables to describe the biophysical fire environment, and then of interest to us are these variables that we use to characterize fuel treatments in previously burned areas. And then lastly are some variables that describe other aspects of the landscape that we thought would affect the relationship between encounters with previous fuel treatments in burned areas on daily fire suppression costs. So if we focus in on the management context of the fire environment, you'll see the first 6 rows there are variables that we use to describe the type of incident management team that was managing a fire on any given day. Recognizing that different hierarchies of the incident management team are likely going to have access to different resources. It's also going to reflect fire complexity. And so we wanted to include that in these models, where IMTUC is a binary variable that equaled 1 if a fire is managed under unified command. Fires that typically are managed by multiple jurisdictions and different agencies. And then ranging from type 1 team all the way down to local management. Those data were derived from investigations into the daily ICS 209 fire reports. Next, we derived a variable called POP, which was just a simple binary variable equaled 1 if a fire intersected a populated area. And we defined populated area using the population data set from Landscan, the Landscan population data set, which comes from the Oak Ridge National Laboratory. Previous studies within this research body have been able to use county-level cadastral data to map the approximate location of private structures, which is great. We were hoping we could do something like that with this study, but because we wanted to span lots of different ecosystem types across large spatial extents, we found that that approach was just simply infeasible. The Landscan data has been used successfully in previous investigations of large-scale risk assessments, and so we thought it would be sufficient here also. Next, we included a variable called remote, which is an index that kind of summarizes or characterizes the relative amount of wilderness and other protected areas within a window surrounding every point in space. This was derived in-house from some colleagues of ours. The idea being that areas located within the core area of wilderness and other protected areas are going to have a higher index value. And as that spreads into areas farther away from wilderness and protected areas, that index value will go down. And these values range from 0 to 100. So next is the biophysical fire environment. We were really interested in including a variable to represent topography that summarized the variability in landscape features throughout the fire perimeters. And so typically topography has been represented statically, for example, the elevation at the point of ignition for a fire. There's a variable that's oftentimes used in landscape ecology and other fields called the topographic position index, which is an index that describes relative slope position ranging from ridge top to valley bottoms. But again, we were interested in looking at the variability in those features within the fire environment. So we first computed the topographic position index, and then within the daily footprint of the fire, we computed the standard deviation of the TPI, included that in our models. Next is a variable that's entitled fuel. It's important here that not to get that confused with the fuel treatment variables that we'll talk about here in a second, but more so fuel loading. And this was, we computed the normalized difference vegetation index for each of our fires, the NDVI. The NDVI can serve as a proxy for pre-fire fuel loading. So we went in and grabbed 1 year pre-fire Landsat imagery within a predefined fire season for each of our fires. Using all cloud-free images, we computed the NDVI, and we included the average NDVI values in this model. Next is the energy release component, which is simply the percentile of available energy per unit area within the flaming front. This is Matt Jolly's data set. So we first converted the raw ERC values into percentiles. we typically talk about ERC percentiles here in fire management. And then we included the average ERC, the average daily ERC within the fire perimeters. So it's important here to also note that ERC varied both across space and across days of the fire. So next are the variables that were important for us. The first is what we're titling Rx, and that equals 1 if a fire intersected a previously treated area, or 0 otherwise. Again, the fuel treatment data that we leveraged was that publicly available geodatabase from line fire. And then next we included another binary variable, fire, which equaled 1 if a fire intersected a previous wildland fire, previously burned area. But we also realized that there were other features that could affect the relationship between fuel treatments and daily fire management costs. And we grouped these here in this landscape context heading. So first we wanted to just make sure that we distinguish the fact that fires that burn in the western United States are arguably fundamentally different than fires that burn in the eastern United States. So we made that first distinction. We created a variable called east, which equaled 1 if a fire was located in those eastern US ecoregions, 0 otherwise. And then we defined 2 more landscape variables. The first one we called low pop. And low pop equaled 1 if there was less than 500 people within 5 kilometers of the final fire perimeter. The idea being that the relationship between encounters with fuel treatments and previously burned areas on daily fire management costs might be affected on whether or not those fires are located in relatively high or relatively low populated areas. And lastly, we derived a variable called low Rx. This is another binary variable that equaled 1 if less than 3,000 hectares of previously treated or burned areas were present within 10 kilometers of the final fire perimeter. The idea being here is that we'd like to be prioritizing the location of fuel treatments in the highest risk areas. And so we may be seeing a different response to encounters with previous fuel treatments and fires in areas that might be deemed higher risk. And the way that we've tried to capture potentially that higher risk is through this variable low Rx. You can think about this being, fuel treatments being prioritized in municipal watersheds or around other sensitive T&E species. So this variable tried to capture some of that potential nuance. So we put all that information into what's called a fixed effects panel model. And this is a stylized equation of that model, where our response variable was estimated as the logarithm of daily fire management costs. And we explained the logarithm of daily fire management costs as a function of 3 large variable groups. Like I was saying, the management context of the fire environment, the biophysical fire environment, and then lastly, those fuel treatment variables of interest. So the panel in the panel model simply just refers to the fact that we have a cross-section of fires, so a whole bunch of fires, and then we also have a time series dimension of those fires where we have daily observations for each fire. And so we leveraged the time variation of our data to estimate marginal effects of our variables of interest. The fixed effects part of the fixed effects panel model is represented by this alpha I, which is a fire level fixed effect. And simply put, the fire level fixed effect recognizes that there are structural differences that vary across these fires, but don't vary through time. And so the fixed effect can remove all the time invariant heterogeneity across those fires, and it allows the error term then to be correlated with our variables. The point of all of that is that it allows us to unbiasedly estimate our coefficients of interest, which is, of course, the goal here in this modeling exercise. So it wouldn't be right to not share just nasty regression outputs with you guys. Economists, we love doing this. The point of this first slide right here is to show that we estimated a whole bunch of model specifications. I'm presenting 3 of those here in these 3 different columns. We had 985 daily observations across 56 unique fires. And overall, we were able to explain roughly 65% of the total variation in daily fire management costs. Now, we're going to focus in here on this 3rd column, which includes the full range of interactions between our treatment and our landscape context variables, as well as all those other variables that I previously described. We're also, furthermore, I should really make note here before I get ahead of myself, excuse me. The values that are not in parentheses are the estimated coefficients from the model, and the values in parentheses are cluster robust standard errors. So moving forward, we're just going to be talking about the third column here, and we're only going to be discussing the outcomes and interpreting the marginal effects for variables that were statistically significant. So when we zoom in on that, let's first talk about the first 5 variables, these incident management team variables. They are jointly statistically significant. 3 of the terms are significant at p-values less than 0.1, 0.01, the 1% level. The sign of the coefficients here is interesting. So the base case here, all these coefficients are interpreted as relative to a base case. So the base case here is a fire that was managed by a type 1 incident management team. And these negative coefficients for fires that were managed by a type 2, type 3, type 4, or local management suggest that relative to days when a fire was managed by a type 1 team, we saw a decrease in fire management costs on days when fires were managed by one of those teams, holding all else constant. It's also interesting also to see that the order of magnitude increases as you go down in hierarchy towards local management, with local management being the least costly relative to a type 1 team. Unified command was positive but not statistically significant. The fires that we had that were managed under unified command, complex, large fires, so it makes sense that that sign is positive, but it's not statistically significant. So next we'll move on to POP. Again, that variable was a dummy variable for days in which a fire burned into an area that was populated by humans. It's positive and statistically significant at the 5% level. And so the interpretation of that is that given that a fire burned into a populated area is associated with a 26.5% increase in daily fire management costs, holding all else constant. And we can evaluate that value at the mean of daily fire management costs, and it translates to roughly $150,000. Next is remote, which was positive and statistically significant at the 1% level. So what that says is that as a fire spreads into areas that are more remote, as we define using that index, we see an increase in fire management costs, holding all else constant. When we interpret the marginal effect, it's a 1 unit increase in that remoteness index is associated with a 13.5% increase in daily fire management costs, holding all else constant. That translates to about a $77,000 increase at the mean value of daily fire management costs from our sample. Next is ERC, which is positive and statistically significant at the 10% level. And the interpretation of that variable is that as a 1 unit increase in ERC, which again, ERC was computed as percentiles. So a 1 percentile ERC increase is associated with a 2.4% increase in daily fire management costs, holding all else constant. And that translates to roughly $13,000. And so next, we're going to talk about our fuel treatment and previously burned variables. And we first look at RX. RX, again, is defined as 1 when fire is burned into a previously treated area. And that was positive and statistically significant at the 10% level. However, the interaction between RX and east is negative and statistically significant. So in order to appropriately interpret the marginal effect of a fire burning into a previously treated area, we need to control for the fact that there are statistically significant differences if, depending on those fires were located in the eastern United States versus the western United States. So for fires located in the eastern United States, when a fire burns into a previously treated area, we estimated a 40.67% decrease in wildland fire management costs, holding all else constant. However, if those fires were located in the western United States, we estimated a 53.6% increase in daily fire management costs, holding all else constant. And now moving on to fire. We can see that our estimated coefficient for fire is positive and statistically significant at the 1% level. And we also found a negative and statistically significant interaction between days in which a fire burned into a previous fire if those areas were defined as a low populated area. That was negative and statistically significant at the 5% level. So again, if we want to interpret the effect of a fire burning into a previously burned area, we need to make sure we control for the fact that there are differences in whether or not that fire was located in a high or a low populated area. So for a high populated area, we estimated a 62% increase in daily fire management costs on days when a fire burns into a previously burned area, holding all else constant. That translates to just over $350,000 when evaluated at the mean of daily fire management costs. However, we see that there is this moderating effect on whether or not a fire was located in a less populated area. So for fires that were located in a less populated area, we estimated a 3.54% increase in daily fire management costs, holding all else constant. So just to say that one more time, a 62% increase in daily fire management costs when a fire burns into a previous fire when it's not in a low populated area. And if it is in a low populated area, that effect goes down to a 3.54% increase. Nice job, everyone. We made it through a regression table. What does this all mean? How are we thinking about it? How are we trying to explain that we saw this, on average, these positive associations between daily fire management costs and encounters with previously treated or burned areas? That was something that was counterintuitive to our expectations and to our hypothesis. However, I think that if we sit back and think about it, I think that there are several logical and rational explanations for that. The first off is we need to remember that our 56 fires are unique in that they all were managed by a type 1 or type 2 incident management team at some point in time. So these fires we can think of as being relatively complex. And so when a fire burns into these previously treated or burned areas, we think that we might be leveraging those as safe and effective platforms for suppression operations relative to untreated areas. We might be thinking that we will be more successful in engaging and managing the fire when a fire hits those areas relative to untreated areas. So we could actually be allocating additional resources on days in which that happens in effort to gain more control of the fire. However, that effect wasn't uniform across our sample. We noted that there are these important landscape context variables that had moderating effects on this positive association between daily fire management costs and encounters with treatments in previously burned areas. The first one being, in terms of fuel treatments, we saw this strong geographic effect, where fires located in the eastern United States, we actually saw a net decrease on days in which a fire encountered a previously treated area. And then in terms of previous fires, we saw that there was a strong effect of rural areas or less populated areas on fire management costs. So on days when a fire burned into a previous fire in these lower populated areas, we only estimated a 3.54% increase in daily fire management costs. So the net effect is still positive for those fires. However, it's at 3.54%. We might say that that's not economically significant. There's some good work out there that showed recently between, I believe, 2010 and 2012, that over 1/4 of large air tanker drops were within 2 kilometers of the wildland urban interface. So that kind of is an additional little bit of context for why we think that we might be allocating more effort or having different effort allocations for fires that burn into previous fires, depending on the distribution of human populations surrounding those fires. And ultimately, it was kind of fun. The data that we used to explain variation in daily fire management costs, we made sure to do our best in that it was nationally consistent, because we didn't want to introduce any, we didn't want to have the variables that describe daily fire management costs to be derived from different sources across our fires. So ultimately, they performed well. And the variables that we included to describe the incident management teams managing these fires were important, which is consistent with some really great work that's come out recently. And it was nice that we were able to include that information in these models. It goes without saying, there's in any of these empirical approaches that are very data heavy and modeling exercises, there's important limitations that we need to consider when we place these findings in any sort of broader context. Like I just said in the last slide, we had a very censored sample of fires where the ISWE data are only retained for type 1 fires that were managed by type 1 or type 2 incident management team. And so what that means is that we weren't able to include fires that were, our wilderness type fires, for example, that are managed by local teams. Those fires are simply not included in this sample. And so we're unable to sort of evaluate or include the full range of fire management responses. We might only be including fires in this analysis that had the management objective of minimizing area burn. So next is that the likelihood, the probability of a fire encountering a treatment or a previously burned area is not random. And in economics, we think of that as a selection bias. That basically the properties between fires that are considered treated or fires that burned into treatments or previously burned areas are different than fires that did not burn into treatments. And we were unable to fully control for that. And so the selection bias can influence the estimated coefficients of the variable that might be that might have the selection bias. In this case, are variables of interest. So it's important to keep that in mind. And lastly, we were due to the spatial scale of analysis here, we were forced to kind of make relatively simplistic characterizations of the daily fire environment. What I mean by that is that we summarize the spatial data within the footprint of the fire, as opposed to understanding where within that footprint we actually did allocate unique suppression resources. And David, Hari, and others have been analyzing and collecting relatively fine scale suppression resource use data for a few years now. And they've shown, they've been doing some really good work that have shown the utility of collecting such fine scale suppression resource use data. And so I think that that's something to keep in mind here. And lastly, we chose somewhat arbitrary thresholds to define those thresholds for the landscape context variables, the low pop and the low RX, and those were driven, by our data, and so there wasn't a whole lot we could do about that. But we definitely need to acknowledge that those changes in those thresholds could have an impact on the subsequent interpretation of those interaction terms. So where do we go from here? Like I said, I think it's really important to sort of scale up these analyses to evaluate a broader range of fire management responses, not just those managed at one point by type 1 or type 2 team. I also think that we need to think about the longer time frame that's important here, right? Like, I think it's interesting in that we might not actually be seeing feedbacks in terms of changing landscape structure patterns on future fire management decision making. That is, maybe we're just not quite to the point yet where we've implemented enough treatments and enough area burn has interacted with those treatments such that we're seeing changes in future fire management costs. It's also possible that there are lots of other constraints on fire management decision making and daily fire management costs that override the influence of fuels or the spatial pattern of fuels. And I think that's something that would be really interesting to explicitly consider. Treatment type, time since treatment, the spatial pattern of those treatments, we're all unable to include in this analysis. It's all things that are important and that we recognize are going to have an important effect. We really were limited by our sample, but things that I think are absolutely necessary to include in future modeling exercises. There are some cool techniques in the non-experimental literature, non-experimental statistical literature from medicine and econ and psychology that try to create samples of very statistically similar units of observations, but only vary in whether or not they quote unquote receive a treatment. And so those can be broadly considered propensity score matching techniques. And that's something that we're currently pursuing in a little pilot project looking at fire duration. And I think that there are other modeling approaches that you could use that you don't have to evaluate this at the daily fire level. You can look at total fire management costs, which we have a lot more of that data out there. We could try and pair fires that burned into treatments or previously burned areas with very similar fires that did not burn into treatments or previously burned areas. And then we could better identify the unique effect of those encounters. Lastly, I think that there's a whole lot of room to think about qualitative approaches to understanding the link between fuels management and fire management. And we can use that information to then inform larger scale quantitative studies such as the one that we tried to do here. So if we go back to our original research objectives, and we just focus in on this first hypothesis, we thought that encounters with fuel treatments or previously burned areas would result in a decrease in daily fire management costs. We didn't necessarily find that. Remember, the only net decrease that we saw was for fires that were located in the eastern United States and when those fires interacted with previously treated areas. Next, if we focus in on the second hypothesis, the effects of fuel treatments in previously burned areas on daily fire management costs differ. In some ways, the average effect was positive, though, for both of those types of encounters. However, what's important is that the landscape context had different effects for the different encounters. Remember, low areas being important for encounters with previously burned areas, and only geography having a role in terms of fires interacting with previously treated areas. So wrapping this up, I think we did our best job to link daily fire management costs with the spatiotemporal progression of fires. And we were able to capture changes over space and time in the fire environment and link that into daily fire management costs. However, the effects of encounters with those treated and previously burned areas were nuanced, right? The landscape context had important effects, and there's a whole lot of room to grow with this. Improving our understanding of the other various constraints on fire management decision-making is very important. And lastly, these analyses are absolutely contingent upon consistent access to fine-scale fire management cost data. That daily fire management cost data, it's a treasure trove of information that we can use to explore these types of questions. However, it's not relatively easy to gain access to those. And I hope moving forward into the future, we can try to pursue data transfer in terms of daily fire management cost data so that we can continue these types of exercises. With that, once again, I want to thank Helen, Sean, and Carol for being co-authors in this project, and I'd love to answer any questions that you guys have. Thanks a lot for listening.
Great, thanks, Kevin. We do have time for a question or two. If anybody has a question, they can type those into the question pane on the control panel at the right. And it looks like we have a couple. One second, All right, here's one question for you, Kevin. Do you really think local governments will enact zoning laws?
And it looks like there's some more kind of context with that. I mean, I want to first just say that it's definitely not my realm of expertise and not something that we necessarily looked at here. I would venture to guess that answer is absolutely going to vary across the landscape, right? Across different local governments. That's something that there's a lot of people. For example, the folks at Headwaters Economics are really interested in this idea of shifting the incentive structure and the relative benefits and costs of fire management to try and reduce it from being the cost burden at the federal level and the benefits at the local level, to try and realign those costs and benefits. I agree. What is the incentive for them to do so? Well, I'm not sure right now. So I don't want to speculate too much about that, but there are definitely a lot of people in this field who are very interested in that exact question.
Great, thanks, Kevin. It doesn't look like anyone else has submitted any other questions. I have one for you that I thought of. So I think in your concluding slides, you mentioned that other variables to consider would be time since fuel treatment or previous fire. Did you have a cutoff for your previous fires and fuel treatments in terms of time or type that you made the decision to include or not include for this study?
No, it's a great question. And the range of fires range the MTBS data set. And so we didn't exclude any of those interactions based on a time cutoff for either of those data sets. The fuel treatment data, however, only ranged from, I believe, 1999 through 2012. And so we're not looking at a really long time frame of previous treatments. Absolutely, if treatments were enacted in the 70s and the 80s, those would have fundamental different effects on treatments that were implemented much closer to the time of a future fire. So the 13-year gap there is important to consider. It's not incredibly long, but it's going to have an effect. I think that the longer fire interval, however, is probably going to have a stronger effect. And that's also going to vary across different ecosystem types, right? Where vegetation recovery and then future management responses are going to change between the Southwest and higher elevation Northern Rockies systems. So it's important to consider, and it's important to recognize that those effects are going to vary between ecosystem types.
Great. Thank you. And it looks like we've made it through questions. So as you close the webinar, a brief 4-question survey will pop up. We really appreciate everyone's feedback. If you have any more questions regarding this webinar or have requests for future webinars, please email or call me anytime. Thank you all for your participation today, and thanks, Kevin, for a great presentation, and have a great rest of your day, everyone.